Continue on physical chemistry. We're in chapter 18, section 7 now. Now we're going to talk about the time-independent Schrodinger equation. An isolated system means external forces are not changing with time. For an isolated system, such as one atom, one molecule, whatever the system is, the force acting is a function of just F, X, Y, and Z, not time. And then the potential energy is also a function of just X, Y, and Z, not time. So we end up with minus h bar squared over 2m times the second derivative of psi with respect to x plus the potential energy as a function of x times psi is equal to minus h bar over I times the partial derivative of psi with respect to time. Now remember, this was time dependent. So we need to substitute out these two to get the time independent version. So remember, psi is a function of x and t. Obviously we're talking about one dimension right now. So we get f of t times psi of x. So f of t is the function of time only. Psi of x is the function of position only. And then psi of x is not time dependent. Remember, this is capital psi, this is lowercase psi. Now remember, capital psi is not equal to lowercase psi. Time dependent, time independent. So we have the second derivative of psi with respect to x squared is equal to a function of time times the second derivative of lowercase psi with respect to x. So we can only, this is only in one variable or dimension, so there's no need to put the other del symbol for partial derivative. So we get the partial derivative of psi with respect to time is equal to psi of x times the derivative of this function with respect to t, f over t, just in case you can't read my own handwriting. So we get minus h bar squared over 2m times this function of time times the second derivative of psi with respect to x plus the potential energy of the function of x times the function of time times this independent psi of x is equal to minus h bar over I times psi of x times the derivative of f with respect to t. So we're going to divide by f of t. So we get derivative of f with respect to t is equal to f prime t. Now we get minus h bar squared over 2m times the second derivative of psi of x with respect to x plus potential energy as a function of x times psi of x is equal to minus h bar over I times f prime of t over f of t times psi of x. And then we get minus... Oh no, there's more. This is okay. So this here, this minus h bar over I times f prime of t divided by f of t, this is equal to constant. Energy is defined as minus h bar over I times f prime of t divided by f of t. So this term here, this is energy. So we get minus h bar squared over 2m times the second derivative of psi of x with respect to x plus the potential of x times the psi of x is equal to energy times psi of x. We're going to call that equation 1. Now remember, lowercase m is the mass of the particle, and that's the time-independent Schrodinger equation. Now remember, E is the total energy, which means the kinetic energy plus the potential energy. And of course, h bar is equal to h over 2 pi. Now that's in only one dimension. Now if we have n particles in 3 dimensions, then we have minus h bar squared over 2m1 times the partial derivative of psi with respect to x1 plus the partial derivative of psi with respect to y1 plus the partial derivative of psi with respect to z1, etc., minus all the way to h bar squared over 2 the mass of particle n times the partial derivative of psi with respect to x of position, of particle n, plus the derivative of y with respect to the y position of particle n, plus the second derivative of psi with respect to the z position of particle n, plus the potential energy times psi is equal to the energy of psi. So we get potential is equal to potential as a function of x1, y1, z1, x2, y2, z2, etc., all the way to xn, yn, zn. And that's time independent. So we get psi is equal to psi of x1, y1, z1, x2, y2, z2, all the way up to x sub n, x, y, n, zn. So the the potential is dependent on the particle's position. So E is kinetic and potential energy for all particles in the system. It's a summation. So this states having a definite energy for which the probability distribution is independent of time are called stationary states. Now for stationary states, the absolute value of psi, capital Psi, with the second derivative with respect to time is equal to 0. And the second derivative of lowercase psi, the absolute value of psi with respect to time, is equal to 0. So oh, that's weird. Should that be t squared? I'm going to put a question mark there. I'm not sure this is right. 2, question mark, 2. This should be the second derivative, right? Okay, so that's the probability distribution doesn't always change with time. For example, but the particle can still be moving. Just the energy is constant with time. So we get capital Psi is equal to E to the minus I times E times T divided by H bar times psi of x1, y1, z1, blah, 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 up to xn, y1, zn. Now the absolute value of capital Psi squared is equal to the absolute value of lowercase psi squared. So, lowercase psi and capital Psi, they must be one single valued, which means a function. They can't be shaped like this loop because it fails the vertical line test. They must be continuous, no gaps. Like in this example here, see there's a hole that has a gap. That doesn't make any sense. 3, quadratically integrable. What that means is there has to be a finite area underneath the curve. So the integral over all space of psi squared d tau, remember tau is all space, has to equal a finite number. So it can't be a parabola because the area under the curve is infinite. So if f of x were x squared, then the integral from negative infinity of f of x squared is going to be minus infinity x fourth of x fourth dx. So we get 1/5 x fifth evaluated from minus infinity to infinity. So you get infinity minus negative infinity, just infinity. That doesn't make any sense. So f of x equals x squared is not quadratically integrable. If a function does meet all three of those criteria, then we say the function is well behaved. The wave function, which meets all of the above conditions, is said to be well behaved. Psi is well behaved, but only for certain values of E, energy. So psi is equal to psi of x1, y1, z1, etc., xn, yn, zn, and E, energy. Now for an isolated system, in other words, not influenced by external fields like an electric field or magnetic field, such as a molecule or an atom, then potential is independent of time and the system can exist in a stationary state. For an isolated system, there may be several stationary states, each represented by wave function psi.